In November of 2025, a radio telescope array in South Africa detected something coming from an object more than 200 million picked up from it before. Not light, not a shape. A signal arriving in radio wavelengths from an object that had already spent months generating headlines, speculation, and genuine scientific disagreement about what it actually was. Picture the moment researchers first noticed it in their data. A faint, specific dip in background radio. Brightness, nearly invisible amid months of failed attempts and noisy readings, appearing for the first time exactly where the comet was supposed to be. Before anyone could say what that signal meant, scientists needed to rule out every explanation that wasn't simple physics. This is the story of the radio signal from 3I Atlas, why researchers moved quickly to investigate it, and what the investigation actually found once the data came in. To understand why any signal from this particular object drew such immediate, careful attention, you first need to know what 3I Atlas already was by the time this detection happened. Discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System, a network of telescopes built to scan the sky for objects that might threaten Earth, it was quickly confirmed as only the third interstellar object ever detected passing through our solar system, following Oumuamua in 2017 and Borisov in 2019. Each one confirmed by the same telltale sign, and orbit so wide and so hyperbolic that it could only make sense for an object that arrived from outside the sun's gravity entirely. Unlike those two prior visitors, 3I Atlas arrived trailing months of increasingly detailed, increasingly strange scientific findings. Researchers had already confirmed it was carbon dioxide rich rather than water, dominated, unusually old, likely more than 7 billion years, and surrounded by a coma releasing an unexpected mix of gases, including a puzzling nickel signal with almost no accompanying iron, a combination researchers have described as chemically unusual enough to require serious, ongoing investigation. By the time any radio telescope turned toward the object in the fall of 2025, 3I Atlas had already become one of the most closely watched, most publicly debated objects in modern astronomy, meaning any new signal from any instrument was going to receive intense scrutiny before anyone drew a conclusion from it. The radio detection itself came from Meerkat, a large array of radio dishes, operated by the South African Radio Astronomy Observatory, and it didn't happen by accident. Harvard theoretical physicist Avi Loeb, who has spent years searching for potential technosignatures and had already publicly flagged 3I Atlas's nickel anomaly as worth investigating from multiple angles, specifically encouraged radio observatories to point their instruments at the comet, reasoning that its arrival direction and behavior made it a genuinely worthwhile target for radio monitoring, regardless of what the observation ultimately revealed. Earlier attempts by the Meerkat team, conducted on September 20th and 28th of 2025, hadn't succeeded, partly complicated by the fact that 3I Atlas passed into solar conjunction on October 21st, traveling nearly in line with the Sun as seen from Earth, a geometry that made radio observation especially difficult for those particular weeks. It wasn't until after that conjunction had passed that researchers finally caught the signal they'd been trying to detect for months. Here's what actually showed up in the data, and it's worth being precise about it, because the nature of the signal itself matters enormously to understanding why scientists reacted the way they did. This wasn't an emission, a signal actively broadcast outward from the comet in the way a transmitter sends a radio message. It was an absorption signal, a specific dip in background radio brightness caused by hydroxyl radicals, OH molecules, in the comet's coma, absorbing radio light passing through them at a particular, known wavelength near 18 centimeters. The same basic idea as a colored pane of glass absorbing certain wavelengths of visible light while letting others pass straight through, just applied to radio waves rather than anything the human eye can see. That distinction matters because absorption signals like this one are a well-established, decades-old technique for studying comets, entirely grounded in ordinary atomic physics rather than anything resembling communication. When comets approach the Sun, ultraviolet. Sunlight breaks apart water molecules escaping from the icy nucleus, splitting each one into a hydrogen atom and a hydroxyl radical, a process called photodissociation that happens billions of times per second across an active comet's entire coma. Those OH molecules then absorb and re-emit radio light at very specific, predictable frequencies. Frequencies physicists have measured precisely in laboratories here on Earth for decades, part of the same well-understood hydroxyl spectral line astronomers have used to study comets and even interstellar clouds of gas since long before 3I Atlas was ever discovered. Detecting that exact absorption pattern coming from 3I Atlas's coma gave researchers a direct, physically grounded way to measure how much water the comet was actually losing, even at a distance where water ice itself doesn't sublimate anywhere near as efficiently as it does closer to the Sun. Dennis Bodowitz, a physics professor at Auburn University who has studied the detection, explained why a signal built from something as simple as water breaking apart still carries real scientific weight, even once every exotic explanation has been ruled out. Ultraviolet echo in the form of OH from an interstellar comet means reading a note from another planetary system entirely. Direct evidence that the same basic chemistry, water ice cooked loose by starlight, plays out in star systems other than our own. That's not a small thing to confirm, even though the mechanism producing the signal turned out to be thoroughly ordinary. It tells researchers that the raw ingredients for the kind of chemistry life depends on aren't some rare, unique feature of our own solar system, but appear to be a genuinely common byproduct of how planetary systems form and evolve across the galaxy, the same basic molecular building blocks turning up in a system that finished forming long before our own sun had even ignited. What made the detection especially notable to researchers studying it wasn't just the confirmation of water loss, but how much water loss the signal actually implied. The team found a substantial water production rate coming from 3I Atlas, despite the comet sitting nearly 3 times farther from the sun than Earth does, a distance where familiar solar system comets are typically far less active, their ice too cold and too far from the sun's warmth to outgas anywhere near this vigorously. That level of activity at that distance added another data point to the growing picture of 3I Atlas as a genuinely unusual object, not because anything about it defied physics, but because its specific combination of age, composition, and behavior kept turning out to be more extreme than what researchers see in comets native to our own solar system. It's worth being direct about why researchers felt this particular signal specifically needed careful investigation before anyone characterized it publicly, because the answer says as much about the scientific process as it does about the comet itself. By late 2025, 3I Atlas sat at the center of a genuine ongoing public debate, driven in large part by Avi Loeb's repeated public suggestions that its nickel-without-iron anomaly and unusual trajectory might be worth considering alongside the possibility of an artificial origin, a minority position within the broader scientific community, but one that had generated enormous public attention and speculation regardless, fueled by social media discussion, podcast coverage, and a steady stream of headlines eager to frame any new data point from the comet as evidence for one side or the other. Against that backdrop, any new signal detected from the object in any part of the electromagnetic spectrum was always going to require careful, methodical verification before publication, precisely because researchers understood how easily an ambiguous early result could get swept up into that same ongoing public conversation before the underlying physics had actually been confirmed. Investigating the signal thoroughly wasn't a reaction to genuine alarm that something artificial had been found. It was standard, responsible practice, applied to an object already under an unusually intense public microscope, where the cost of publishing something prematurely, only to have it walked back later, would have done real damage to public trust in exactly the kind of careful science this entire investigation was built to demonstrate. That same careful, responsible approach played out in parallel through a completely separate, dedicated search effort that deserves real credit for how rigorously it was conducted. A team using the SETI Institute's Allen Telescope Array specifically searched 3I Atlas for any sign of what researchers call technosignatures, artificial radio transmissions that might indicate deliberate, engineered origin rather than natural cometary activity, drawing an explicit comparison to humanity's own Voyager. Probes, launched in 1977 and still carrying instruments and a message intended for any civilization that might one day encounter them, reasoning that if any other civilization had ever sent a similar probe of its own, an interstellar object passing through our solar system would be exactly the kind of target worth checking. The team scanned across a wide range of frequencies from 1 to 9 gigahertz over more than 7 hours of dedicated observing time. Using a purpose-built search pipeline nicknamed BLISS, the team identified nearly 74 million individual narrowband signal detections in the raw data, an enormous number that sounds dramatic until you understand what it actually represents. The overwhelming majority of those detections were immediately recognizable as ordinary radio frequency interference, signals from human technology here on Earth, satellites, cell towers, and other terrestrial radio noise, rather than anything originating from the comet itself. After systematically filtering out that interference, narrowing the count down to roughly 2 million remaining candidates, and then applying additional localization analysis, using a tool called N-beam analysis to confirm which signals genuinely traced back to 3I Atlas's actual position in the sky, rather than some unrelated source, researchers narrowed the full haul down to 211 remaining candidate signals, worth visually inspecting by hand, one at a time, in the time-frequency domain. Every single one of those, once examined directly, turned out not to warrant any further follow-up. The search came back clean, a genuine, rigorous, negative result reported honestly, rather than quietly buried, published with the same care and transparency as any positive detection would have received. That negative result matters just as much to this story as the positive OH detection did, because together they represent exactly the kind of complete, methodical investigation a genuinely puzzling object deserves. One search, using Meerkat, found a real, physically explainable signal rooted in ordinary photochemistry, confirming active water loss consistent with natural cometary behavior. A separate, independent search, using an entirely different instrument built specifically to look for artificial signals, came back with nothing. Researchers didn't have to choose which result to trust or which one to publicize more prominently. Both were reported, both were explained honestly, and both pointed toward the same underlying conclusion from two completely different angles. There's an additional layer of complexity in 3I Atlas's story that surfaced around the same period, adding yet another genuinely strange, though entirely natural detail to the object's overall profile. Researchers tracking the comet's inner coma across dozens of nights of observation, using the 2-meter twin telescope at Spain's Teide Observatory, identified a distinct jet of material venting from high latitude on the nucleus, visible as a faint, narrow plume once specialized image processing techniques were applied to sharpen fine structural details that would otherwise stay hidden in the glare of the surrounding coma. That jet didn't simply point in a single fixed direction, but instead showed a periodic wobbling modulation, its angle shifting back and forth in a repeating pattern consistent with the jet slowly precessing around the comet's own spin axis as the nucleus rotates, tracked across observations spanning from early August through late August of 2025, night after night, patiently confirming the same subtle drift each time. That measurement let researchers estimate the nucleus's rotation period at roughly 15.5 hours, marking the first time this kind of periodic jet angle wobble has ever been documented on an interstellar object, specifically, a level of physical, structural detail nobody had ever managed to extract from either of the two prior interstellar visitors. It's a genuinely interesting, still being studied feature of the comet's physical behavior, evidence of a lopsided, unevenly active nucleus venting. Material more from certain points on its surface than others as it spins, the kind of detailed structural insight about an interstellar object's actual physical body that scientists had never had the observational tools to gather before. Taken together, these separate strands of investigation, the OH radio absorption confirming active water loss, the SETI search coming back clean, and the detailed tracking of the comet's wobbling jet structure, all converge on the same fundamental picture. Bodowitz and other researchers studying have been willing to state that conclusion plainly. The radio detection establishes, without meaningful doubt, that 3I Atlas is a natural comet, behaving according to well-understood physics and nothing else. That's not a hedge or a cautious understatement. It's a direct, evidence-based answer to exactly the question, the strange signal framing the anomaly out of hand, but by actually pointing serious instruments at it and doing the work required to explain it properly. None of that makes 3I Atlas a less interesting object to keep studying, and it's worth being clear about that too. A genuinely ancient comet, older than our own solar system, carrying chemistry and isotope ratios pointing toward a formation environment, unlike anything in our own cosmic neighborhood, remains one of the most scientifically valuable objects astronomers have ever had the chance to study up close. Its water production rate, its wobbling jet, structure, its unusual nickel chemistry, all represent real, still unfolding scientific mysteries in their own right, each one worth continued observation as the comet continues its outbound journey. What the radio signal specifically resolved wasn't the full mystery of 3I Atlas. It was one narrower, urgent question: whether this particular detection, in this particular part of the spectrum, represented anything beyond ordinary cometary physics. The answer, confirmed through careful, independent verification, was no. So here's where that leaves things. Somewhere out past Jupiter's orbit now, 3I Atlas continues its long, one-way journey back out into interstellar space, carrying with it a body of scientific data more detailed than anything ever gathered from an interstellar visitor before it, including a radio signature confirming, in the most direct terms physics allows, that its water is escaping the same way water escapes from any sufficiently active comet, warmed by starlight. Think about what it actually took to reach that confirmation, because the process itself is worth appreciating as much as the result. Months of failed attempts, complicated further by a poorly timed solar conjunction that blocked observation entirely for weeks. A researcher publicly encouraging observatories to keep trying, aware that a null result was just as scientifically valuable as a positive one. A second, entirely independent team running a separate, painstaking search through 74 million raw signal detections, filtering them down step by step until only 201 remained worth a human researcher's direct attention, and then confirming, one by one, that none of them held up. That's not the story of scientists stumbling onto an easy answer. It's the story of a research community taking a genuinely open, publicly debated question seriously enough to actually chase it down through months of careful, often unglamorous verification work, rather than settling for whichever answer would generate the most attention. The signal that prompted this particular investigation turned out to carry a message after all, just not the kind its framing might have implied. It was a message about chemistry, about a planetary system that formed billions of years before our own sun ignited, written in a language, radio absorption from hydroxyl radicals, that scientists have understood for decades and finally had the right instrument, pointed at the right object, at exactly the right moment to actually read. Whatever 3i Atlas reveals next, as it continues fading from view on its way back out into the dark it came from, will very likely arrive the same way this signal did. Not as a dramatic, unexplainable mystery, but as one more careful, patiently verified piece of a genuinely remarkable, entirely natural story still being pieced together, one confirmed observation at a time.